An extraordinary sequence of events is unfolding at this very moment. Come September 2025, our planet encounters a barrage of close encounters. The asteroid designated 2025 FA-22 will glide by at slightly more than double the Moon's distance, whereas 2025 RJ-2 hurtles in even nearer, under 300,000 kilometers from Earth. Numerous tinier bodies are cataloged within sublunar ranges during one unprecedented week. Simultaneously, 3I/ATLAS, an interstellar comet with unusual chemical makeup, races toward Mars along a path absent from the minor planet since historical records. The sheer volume challenges statistical expectations. Could this be mere chance in the cosmos, or might it signal a trend that reshapes our strategies for safeguarding Earth? Such revelations could alter our role as mere observers in the solar system. The month of September 2025 brings a continuous barrage of warnings. Experts at the Minor Planet Center record asteroid 2025 FA-22 passing at roughly 2 times the lunar distance, approximately 835,000 kilometers away. 3 days prior, 2025 RJ-2 zipped past at a tighter margin, just 0.78 lunar distances or fewer than 300,000 kilometers. These incidents don't stand alone. From September 12th through 18th, the tally breaks every past benchmark. No fewer than 28 near-Earth objects venture inside the Moon's orbital path. This marks 3 times the previous weekly peak. The majority measure between 8 and 25 meters, objects capable of burning up on re-entry or detonating akin to the Kelebinsk event. Yet FA-22 and RJ-2, both sizable with potential widths reaching 120 m, warrant worldwide scrutiny. Every spotting alerts monitoring networks instantly. Facilities like Pan-STARRS in Hawaii, Atlas in Chile, the Rubin Observatory in Chile's Atacama Desert, and Catalina in Arizona capture the signals. Information pours from robotic scopes, sifted by algorithms designed to spot the dimmest, swiftest specks. The rhythm shows no sign of slowing. Fresh discoveries get identified, monitored, and documented often mere hours after initial sighting. The Rubin Observatory, freshly operational for months, delivers a torrent of new insights. Its Broadview imager scans vast sky sections in broad sweeps, detecting threats that evaded notice only a year ago. By the numbers, this should occur once every few decades. Adjusted models accounting for observational biases estimate the likelihood of over 25 sublunar NEOs in 1 week at under 1 in 1,500. Despite enhanced tracking, the September uptick remains anomalous. It forms a grouping that bucks the typical haphazard distribution of asteroid flybys. A few specialists hypothesize influences from orbital alignments or an undetected fragmentation in the asteroid belt, though most attribute it to cutting-edge tools. Spotting rates for items over 20 m inside 1 lunar distance now top 90%. Gaps in coverage are narrowing, yet persist. Trajectories from the sun's direction continue as a vulnerability, a point driven home by the Kelebinsk atmospheric explosion 12 years back. Online platforms buzz with conjecture over the figures. Graphs spread depicting a peak too pronounced for randomness. Some label it coordinated, viewing it as a cosmic alert or harbinger. Within academic communities, responses stay tempered yet vigilant. Every near approach gets documented, scrutinized, and stored, bolstering a defense network whose effectiveness hinges on the most recent finds. For a fleeting period, global focus turns upward, and the query persists: what if one of these had veered just a bit nearer? Picture if FA-22 had struck true. Spanning 120 m, about the length of an urban block, this rock would commence its plunge from the upper atmosphere, a quiet racing at exceeding 18 kilometers per second. Assuming a rocky composition like many of its scale, it would squeeze the air in front until immense forces tore it apart in a fierce overhead blast, echoing the 2013 Kelebinsk incident. Size plays a key role, however. The Kelebinsk blast shattered panes in 6 municipalities and hospitalized over 1,500 individuals, mainly from shard injuries and head trauma. FA-22 packs over 20 times that punch. Such a rocky body might detonate between 10 and 20 kilometers up, unleashing power akin to multiple megatons of TNT. The resulting pressure surge could raise structures over vast square kilometers. Those proximate to the epicenter might have mere moments to respond. Windows would explode, frameworks would give way, and the thermal pulse could set roofs ablaze. Damage wouldn't confine itself to the impact zone. Peripheral areas would suffer from hurled fragments and failing edifices, amplifying the hazards. Should Fa-22 consist of iron, the outcome shifts dramatically. Iron variants prove tougher and more solid. Rather than breaking up, it might slice through the air intact, slamming into the surface at near maximum velocity. That would carve a pit spanning hundreds of meters, spawn a blaze seen from afar, and hurl debris high into the upper atmosphere. While the immediate strike would wreck local systems, broader ecological effects could extend much farther based on the site. Now, consider an oceanic landing. More than two-thirds of likely strike zones cover water. In that case, the force would generate an enormous vapor cloud and waves of tsunamis would spread out from the epicenter. Although much of the surge's power fades rapidly in the ocean depths, areas along the coast within several hundred kilometers might encounter towering walls of water reaching dozens of meters. Harbors, urban centers, and flat islands would suffer devastating inundations with minimal prior notice. The incident in Chelyabinsk highlighted this vulnerability. Celestial bodies coming from the sun's direction remain hidden from earthbound observatories right up to the final seconds. Sergei Karpov, whose vehicle-mounted camera captured the defining images of that chaotic dawn, continues to recount the chaos through sounds of shattering glass and utter disarray. These days, he collaborates with emergency preparedness groups, encouraging urban areas to practice for surprises that arrive unannounced. His core advice boils down to one point: the boundary separating a benign meteor streak from a catastrophe that raises communities is far slimmer than people generally appreciate. Post-event modeling after every near-miss yields chilling figures. The force of collision, local population concentration, hour of occurrence. All factors in an impartial celestial formula unfolding without purpose or hostility. Preparedness hinges on alertness, prompt identification, and mechanisms that convert alerts into swift responses. Lacking those, the toll tallies up in ruined metropolises and destinies irrevocably altered. Swan offers a contrasting display. Detected on September 11, 2025, not via traditional visual scopes, but through irregularities in solar wind detected by the Swan device on SOHO. This comet's emergence was heralded by an abrupt rise in hydrogen signals. The Lyman alpha glow, a UV signature undetectable without aids, illuminated sensor feeds well before terrestrial spotters thought to search. A few amateur astronomers probing the Virgo region verified the orbital data's implications. Swan was intensifying rapidly, its tail extending twice as long in just one evening. This went beyond mere luminosity. Spectral analysis uncovered a gas envelope laden with volatiles, chiefly hydrogen alongside traces of cyanogen and carbon-based molecules. Ejection rates surged as the comet approached its solar closest point, with hydrogen output exceeding water-ice vaporization by a ratio that surprised veteran trackers. The cause lay in Swan's frozen core cracking apart from intense solar radiation, unveiling new strata and unleashing pent-up gases through repeated bursts. Every fresh fissure in the core triggered additional hydrogen emissions detectable only by UV-sensitive gear. Leading observatories rushed to allocate slots for ongoing monitoring. The Rubin Observatory, in the midst of calibrating its scanning rhythm, allocated urgent sessions to monitor the shifting envelope. At the same time, volunteer astronomers kept supplying inputs to the analysis chain, logging eruption timings, charting tail shapes, and highlighting abrupt luminosity shifts. Their notifications guided advanced spectrometers toward ephemeral features. Streams of ejecta curving from the heart, minor alterations in composition, and indicators of internal strain that frequently signal impending disintegration. As the month of September progressed, the danger of splitting grew prominent. Updated simulations indicated that Swan's core, pocked with fissures, could fail to endure its solar grace. Should it disintegrate, the ensuing fragment swarm might generate a dazzling vista observable from our planet and beyond. For those in asteroid defense, Swan's erratic nature underscored a key lesson. Dangers don't always follow quiet. foreseeable trajectories. Occasionally, the alert arrives via an explosive hydrogen pulse, with initial spotting relying on a worldwide cadre of hobbyists equipped with scopes and detectors fixed on the heavens. The date April 13, 2029, stands out in bold on all asteroid safeguard schedules. That morning, Apophis will skim a mere 32,000 kilometers above Earth's surface, nearer than numerous telecom orbiters, and appear unaided as it arcs overhead. For a long stretch, Apophis fueled apocalyptic press, tagged as a potential world ender initially spotted back in 2004. Yet over time, collision fears have waned, giving way to an exceptional research prospect. A real-time drill for deflection strategies, under global scrutiny with tools primed. This skim goes further than visual drama. Our planet's pull will exert influence on Apophis, stirring not liquid tides but upheavals in stone and grit. Experts anticipate tangible alterations. Slides across the exterior, surface cover dislodged, perhaps a reconfiguration of the object's outline. Such gravitational distortions have yet to be gauged so intimately on an entity of this scale. It forms an organic trial impossible to replicate artificially. To document it, NASA has launched OSIRIS-APEX, a probe set to link up with Apophis shortly post-encounter. Its objectives include recording each mark, repositioned fragment, and hint of our world's unseen grasp. Comparative images from prior and subsequent will disclose how space rocks react to intimate brushes and how minor tugs from gravity can redirect a drifting body. To Andrea Riley, an integration specialist with the Hera mission crew, the nearing event holds deep resonance. In a 2022 journal note, she remembers the unease of following Apophis coverage in the media during her teenage years. That mix of apprehension and excitement about emerging tech now drives her efforts. APEX goes beyond a mere experiment for researchers and probes. It serves as a vital practice run for humankind's capacity to monitor, simulate, and potentially redirect an actual hazard if required. Each computation, each measurement, each program developed for OSIRIS-APEX or terrestrial radar contributes to a tomorrow where near misses are handled with steady accuracy rather than alarm. As APHIS hurtles by, observers worldwide can witness planetary protection at work, transforming a once terrifying news story into one of readiness and exploration. The Comet 3I/Atlas, designated C/2025N1, distinguishes itself right from the initial analysis. On July 1st, Pan-STARRS detected its hyperbolic trajectory, yet the composition profile truly prompted astronomers to vie for slots on the planet's biggest observatories. Preliminary VTX shooter observations, obtained as the comet traversed roughly 4 astronomical units, indicated a coma primarily composed of carbon dioxide rather than water vapor. JWST validated these findings in August, showing carbon dioxide output at 129 kilograms per second, with water lagging significantly at only 6. This creates a ratio of almost 20 to 1. Such a proportion is unheard of for a comet so luminous and vigorous. By contrast, typical comets in our solar system invert that balance, with water release vastly exceeding carbon dioxide. In this case, the standard dynamics are upended. The oddities extend beyond the gases, too. Detailed spectra from the VT's UV tool, gathered across multiple evenings in July and August, revealed a robust atomic nickel signature emitting 4.6 G per second from the coma by August 21st. Iron, however, which usually pairs closely with nickel in comet makeup, was undetectable, dropping under the sensitivity limit. This iron-free nickel occurrence is uncommon, even for objects from interstellar space. Among local solar system comets, nickel and iron generally emerge side by side, released through identical thermal mechanisms. Explanations vary from distinctive origin processes to iron's gradual depletion over eons of interstellar travel. A few theories invoke the decay of nickel-laden organic materials, while others suggest cosmic ray erosion, removing more fragile iron substances. No unified explanation captures the full evidence so far, though discussions remain heated and unresolved. Midway through August, yet another revelation emerged. The Mars Reconnaissance Orbiter, probing in ultraviolet bands, spotted an abrupt surge, a burst that intensified the comet's glow more than twofold within under 36 hours. Earth-based light measurements indicated the tail fragmenting into various streams, with dust flowing in divergent paths. These irregular surges diverge from the typical jets powered by water. Rather, they suggest reservoirs of carbon dioxide or similar compounds bursting forth as solar rays infiltrate new cracks. Investigations into its spin deepen the mystery. Brightness variation studies imply a leisurely, perhaps irregular nucleus rotating on an axis that varies periodically. The cycle exceeds 22 hours, accompanied by minimal luminosity shifts. This points to an almost round form or intricate rotation not aligned with primary axis. Consequently, forecasting surges and tail changes becomes all the more challenging. Every fresh batch of information heightens the fascination. And as perihelion approaches on October 29th, global spectroscopists are in a sprint to document each nuance before the comet vanishes into the solar glare. At present, 3I/Atlas persists as a compositional anomaly, a leisurely rotating envoy from a more frigid, shadowy region of the cosmos.